You are tuned into Mostly Humans. The opinions and views shared by the hosts of this podcast are uniquely their own and do not reflect the view or opinions of the companies they work for. P.S. Don't sue or fire us. Thanks so much. Now let's get into the episode.
I'm not even mad because it was so audacious. The brother walks up right after, looks in the Ring camera like this, grabs the whole bowl, opens his pillowcase, and while he's looking at the camera, pours it all in and drops the bowl back down and goes, "Happy Halloween," and just backs away. And I was like, the most savage thing.
All right. Welcome back to Mostly Humans. I am Justin Wright. I'm joined by my very talented and well-coiffed co-host, Matt Bigelow. How are you doing this week, Matt?
Always coiffing, so that the people will never know what my hair naturally looks like without Elmer's glue in it. I'm your human agent and your human host.
Look at that.
Yes. Cute little sticker that we have. We got some t-shirts made as well at my company that say human agent on them. And they're a real hit when you walk around with them because people are like, yeah, it's a very common joke to be like, I'm not AI, I'm real. Goes over well.
And despite the topic today, we are still real. This is still us manually recording and talking to you as human beings. But one of the things that we talked about wanting to explore is kind of a two-layer topic. One is, how do LLMs actually work, which I think is something that's worth digging into a little deeper, because now that a lot of people are using these tools, there's still a lot of mystery in terms of what is this magic black box actually doing. And then we're going to talk a little bit about how that translates to image and video generation, which is part of the same process, but slightly different. And so we think digging into this a little deeper will be an interesting topic. But before we dive into that, any fun learnings this week or fun off-topic things from this last week?
Man, yeah. So it's Halloween today and like right now. So you all are probably hearing this like it's almost Thanksgiving by the time you're hearing this. Happy Thanksgiving, folks. But it is Halloween right now, and it's about to be trick-or-treating time in my neck of the woods. And I do have a funny anecdote for you. So we have dogs who do not do well with noise or humans or dogs being on TV or bells ringing, anything.
That's a lot of categories.
Yeah, all the categories. Everything's just a whole bunch of drama. If there's ever a slightest noise, like the air conditioner kicks on, they're like, "What the heck was that?" And like, they're just so
Intruder.
So it's like, guys, nothing as ever bad has happened to you your entire lives. You completely coddled. Why is this so ingrained in you that there's always trouble? So we choose to close the blinds and put up a sign, leave a bunch of candy out there. We're generous, but we just can't, unfortunately, have the doorbell ring and then see all the cute little costumes and stuff and then say hi to the kids because our dogs would jump out and freak out with the masks. Disaster. So this is what we do. Unfortunately, we're those people, the lame people that leave the bowl out and say, "Don't take the whole bowl, please." Now, there is a savage that came to my neighborhood a year ago. Total savage.
I love where this is going.
I'm not even mad because it was so audacious. So a little girl, she's probably like 9 or 10, and her seemingly 3 year younger than her brother walk up our stairs in their costume. And you can see on our Ring doorbell, when I saw it, she was like, "Only take 3 to 4 pieces of candy, like say some for everyone." So she like does her thing. The brother walks up right after, looks in the Ring camera like this, grabs the whole bowl, opens his pillowcase, and while he's looking at the camera, pours it all in and drops the bowl back down and goes, "Happy Halloween," and just backs away. And I was like, I'm not even mad. Like, he played to the camera. He didn't break eye contact. It was the most savage thing I've ever seen. And that kid made me laugh for almost a whole year.
That's unbelievable. What you could do, so speaking of anecdotes from this last week, you could buy one of these or pre-order one of these $500 a month humanoid robots that are AI powered that got announced on Twitter, because I still refuse to call it X, this last week. And it's like the most amazing launch video of all time. And then basically somebody found out that all the robots were actually just being remotely controlled by humans somewhere else for the entire demo video. And they're not actually real AI robots. So you could buy one of those and then have the remote control human giving out your candy and maybe shooing away the whole bowl candy kid.
I'm really curious. Like, tonight's it's a year anniversary since this went down. Like, is he going to come back just as strong? Like, if he did, is it still funny, or am I now upset? Like, lot of anxiety building right now.
I couldn't be upset about that. The eye contact with the camera. It's like there's that video that I've seen floating around the internet of there. It's like a chipmunk or a hedgehog that would eat the guy's crops, and it would always face the camera while it was eating his like strawberries and stuff. So it's it kind of reminds me of that. Well, so either way, I think you're gonna have an interesting Halloween, whether or not this incredible human shows up again. But we're talking today about how LLMs work, and there's a ton of complicated math that explains how they work. And machine learning engineers will talk to you ad nauseum about all the different math equations and embeddings and all these things. And our goal today is to simplify some of this stuff so you can actually understand how some of these things work. And before I dig in, I would love to get your perspective, Matt, on, your understanding of how LLMs work and kind of high level, because I think you have really good analogies that I always wish I thought of.
Oh, I don't know if I have analogies for this one, but I'll tell you what I know. And my perspective is solely around text. So think ChatGPT, think chatbots, stuff like that. And then I don't really know much about video or image generation, so I'm excited if you have some information to share with us. We can all learn. But I'll tell you guys how I understand it. So computers have always been ones and zeros, basically all of computation. It's ones and zeros. It's code. It has a defined answer and outcome. It's deterministic. So think about, some people say like, oh, I'm really bad at math, but I'm really good at English, right? I could write a paper all day and I get A's on all my papers and I'm constantly getting C's and D's in math. And why is that? Well, language, writing, English it's not deterministic. A paper is not right or wrong. It's interpretive. It's subjective. You can have an opinion about it, right? Science, math, STEM, all that kind of stuff, there is a defined answer, right? And some people just kind of work better with language. We've all gotten really used to how we interact with computers pre-LLMs, meaning that we know that we have to type things into fields and select things from drop downs. And we had to find like workarounds called UI, user interface, to communicate with machines. Because we knew we couldn't like talk to it. It just doesn't get it. It doesn't understand it. And what's so interesting to me about LLMs that I think people might find really eye-opening on this podcast is they still can't understand language. It felt like overnight, oh my God, they understand me now. We can just talk to our computers. We can and we can't. What the large language models have done, the way I understand it, by layman's terms, is they've turned all of language into math and then studied all of the words that were ever written. And all of the words and all of the sentences and everything that was ever written in the history of the internet was given a value. And they started to study patterns and think about like probabilities and statistics. You can predict, like when you're watching a football game and you're a New York Giants fan and you have a 99.95% chance of winning 2 weeks ago in Denver and somehow blow it.
Yeah, now it's much lower, unfortunately.
That happened.
It's tough for you guys.
That is predictive analytics saying this is where this will be. So what they did with language is they figured out a way to break down everything into math. And so, for example, the basketball player jumped up and blocked the sun, not likely. The basketball player jumped up and blocked the shot, much more likely. And it starts to understand from everything that's written that these words have a numerical value. These phrases have a numerical value. And it seems like numerically, this one is much more likely to happen most of the time. And then what they did after that is they had lots and lots and lots of people doing, basically reviewing what the LLM was coming up with and correcting it and being like, oh no, you said blocks the sun like 20 times. It really should pretty much exclusively be blocks the ball. And then what we now see is as we type into the box, typing into the darn box, we talk about that a lot in this podcast, we are typing in math. We just don't realize it. We see letters on the screen. We can understand letters and we can understand language. The machine cannot. Every word, every phrase, every sentence that we are typing in, what the machine sees after you press enter is a bunch of numbers. And then it's doing probabilities and statistics and predicting the very next word that would make the most sense based off of the things that you said to it. And that's why it feels like it knows what you're talking about. That's why it feels like it can take over the world. And that's why I also don't think it can. Machines still don't understand language. They don't understand it. They understand math still exclusively. And that actually helps me sleep a lot better at night.
Yes. They're not taking over the world yet. No, it's a really good, really fundamental understanding of how this stuff works. And I'm going to throw out a few words that might be scary for the audience, but I promise I'll make them less scary. So, and also for like the deeply entrenched AI people, I'm going to give one example of this. I understand there are many ways to do the things that I'm talking about, so please don't sue us. That's part of the disclaimer at the beginning of the podcast. But some terms that you may have heard thrown around that are part of this process are embeddings, vectors, and vector search. And so I want to talk about what these things actually are. So embeddings are created. It is essentially that process of turning words into language that Matt was talking about. And so when these
words into math, right?
Words into math, yes. Words into language is what they are. Words into math, yes. Thank you. But the way these models are trained is they're fed a bunch of content. And what happens is the LLMs are trained on this content and they start to break down these words into numbers. And then they start to understand relationships of these numbers. If you feed it enough fiction novels, it'll start to understand what types of words appear close to each other or whatever. And so when you ask a question, it breaks down your question into these embeddings, and it then creates a positional relationship amongst these embeddings. So it takes your sentence, it finds the essentially like math number equivalent of each of those words, and then it creates a single embedding, which is all of the words you said, their math values, and then the relationship of what you said. So obviously, if you ask a question to an LLM, the sequence of the words that you used matters. And so it has to understand how those words are positionally related. And then what it does is it turns that into a vector, which, not to get too deep down the rabbit hole, it's basically a line with a direction. And the way that I think about this is if you think about the human language or human language in general as a bunch of words in like three-dimensional space, right? Because there's so many different relationships among words that you can't just put it on a regular like 2D graph and cover all of the relationships. Because if I'm talking about pets, then dog is probably pretty close in space to pet, cat is pretty close. Tiger is probably not as close unless you're like prime Mike Tyson. And then obviously that one's a little closer for you, right? But you're basically creating this line in space and you're seeing where that line is in relation to all of these other lines. And so what it's trying to do is basically just find the smallest distance between those vectors, those lines in space. And so that's how it's essentially going to complete that phrase that you said, the basketball player blocks the shot, because it takes all of those embeddings, basketball, player, blocks, whatever, and it looks at those words in space compared to all these other words. And it says, well, shot is the closest other word here if I actually like measure the distance. And so that's the word that's likely going to come next. And so you'll hear people talk about vector search, and all that means is we're just comparing all these lines. So a lot of people who are using LLMs or training these models, they store all this stuff in a vector database, which again, a database is just a place where you put a bunch of data, and a vector database just happens to contain all of these three-dimensional lines. And you're just trying to measure the distance between these lines as you ask questions. So to Matt's original point, all of this is just math. I'm just saying how close is this line to these other lines, and then that's how it delivers a response. And how we've, what we've mentioned on the podcast before is, well, what does hallucination mean? Hallucinations mean that there's a chance that when you ask something about pets that it's going to pick tiger because Mike Tyson had pet tigers. And so that's probably not the animal you're looking for if you're telling it to write a children's story about pets. But there is always a small chance that you will create a children's story about Tony the tiger because tiger is somehow related to pets. And that's also how LLMs understand, quote unquote, understand language, because you're not relying on just traditional keyword search in these instances. You're actually looking at the relationships of words and phrases. And so that's where people start to assume or think that these language models understand language, because you're pulling all of these relationships amongst words, and you're not just doing a traditional like keyword search of this specific word and it's going to return all the things that have that word in it. And so if people are throwing around these terms at you, all it really means is we're looking at a bunch of lines in space and we're trying to find the closest lines to the line that your question has created. Hopefully that makes sense.
Yeah. So the key takeaway, it sounds like, is when you turn letters and words into numbers, that's called embeddings, right?
Yes, exactly.
Cool. I think that's a key term that everyone should know. Like, you just know it. Like, you might not like it. It might sound like a technical thing. Well, now you need to know it because it's an important thing to understand how this stuff works. I guess my follow-up question would be to you is, we talked about hallucination. And so hallucination, in the way you described it, it sounds like it's when a chatbot, let's say, gives you an answer back that is like clearly wrong in your mind, right? If somebody said like, who was the first president of the United States? And it said John F. Kennedy, that's wrong. It's George Washington. And if it said that, we would call that a hallucination. But based on the way you're describing it, if it ever said something like that, that would mean somewhere in its training, someone said the first president is JFK. And if 99 of us asked it, it will probably say George Washington because those lines, those probabilities that it's George Washington are very, very, very high. But there is a chance that the 100th person that could ask that question might get JFK because it is in the training set somewhere. Is that right?
It is right. And actually the reason something like that would probably happen is because it was trained on something where that's not the full sentence. The sentence might be the first president to do X was JFK. And so what it's doing is it's actually creating the relationship to your query because, again, it understands to some degree the nuance of language because of these relationships, but it's from somewhere there is a sentence that includes first president and JFK. And even though that's not the complete sentence, that is part of the training material that, led to this training of the LLM. And that's also where something called reinforcement learning comes into play. So these models get better over time because correct answers are essentially upvoted, or like, when you go on your social feed and you toss somebody a like for something they posted, you're reinforcing them to create more of that content, right? Like human beings are reinforced by a number of things, and training these models works much the same way, where you reinforce the correct answers. And so you essentially say, hey, do more of this. Like, this is a good answer. The one problem with reinforcement learning is, and this is a little more nuanced, is it rewards lucky guesses the same as it rewards actual correct answers. And so that leads to some biases in some of these models where it may have arrived at the right answer, but followed the wrong vector comparison or whatever. But because it ended up at the same place, you give it a thumbs up, and that might cause some downstream behavior. And so that's part of why these companies spend so much money and time training these models, because you're feeding it a bunch of data, which takes a ton of time and energy. And then you're also reinforcing the correct responses, but then you have to keep monitoring and make sure that that reinforcement isn't actually causing it to do more of the wrong thing, because it's hard to distinguish whether it was a lucky guess or whether it was actually answering correctly in some instances.
That's super interesting. So when these LLM folks, the people who grow these models, say things like, we don't really understand ourselves why it does what it does, that spooks a lot of just normal people, because they're like, whoa, you're growing this thing that seems pretty intelligent. And it is very intelligent. It's just a math wizard, really. It's a probability wizard, and you don't know how it works. I think that freaks a lot of people out when they first hear that. Before I got into the space and before I started to better understand it, I really didn't like comments like that. It was like, to me, it felt like somebody was saying like, hey, we invented flamethrowers, but we have no idea what makes the flamethrower go on or off. And like, it sounded dangerous. That's not really what they meant. So when they say something like that, they're speaking to an audience, like a tech audience who follows what they mean. But for your layman's person, when they say they don't really understand why the large language model does what it does, what are they really trying to say, in your opinion?
Yeah, you're talking about data sets that are so massive that no human being or a group of human beings collectively has ever been able to analyze data on this scale, right? So to take a step back, what really unlocked the progression of large language models to what you see today, because AI isn't new technology, right? There's been AI research going on for a very, very long time. But before, we were limited on the amount of data that you could actually train with because the process took so long. So if you think about we're talking about, training by feeding these models a ton of information. And what it's doing is it's actually creating all of these embeddings to create this sea of possible options, right? And that's what this training process is you're breaking down all these words and phrases and content, and it's creating those embeddings. And because you need something to actually compare what you're saying to what exists. And so the model training is creating those embeddings. Before, technology limited the amount of training that we could do in a given period of time because it was only possible to train it word by word in sequence. So you would have a sentence and you would have to break down that individual sentence word by word, and there's computing power restrictions here, and it would just take X amount of time. In 2017, a group of Google researchers released something called the Transformer paper. And actually, the T in GPT stands for transformer. So fun fact for the people at home. But transformers, basically, all you need to know about that paper is it allowed this training to happen simultaneously in parallel. So now, instead of having to go word by word in sequence, you can actually train it on multiple sentences at the same time. And that allowed us to now feed it way more data than was ever possible because there was no way to actually train these models on the entirety of the internet, before the end of the world, theoretically before. And so when they say they don't understand how it works, it's referring to how it's building these relationships among words. And because it's all probabilities, that the president example that you gave, right? Like, it's hard to understand exactly why it would say JFK is the first president, because it's hard to figure out from that massive data set exactly which source material had, first president and JFK in the same sentence, because it's probably not one source, it's probably many sources. And because you're reinforcing the right answers, there's just too much information there for human beings to actually understand and comprehend. We know fundamentally how it works, the process of how it works, but it's those details of where it created those relationships that it's too much data for us to figure out that level of detail. And so it's not that we don't understand how they work. It's just we don't understand how it builds some of those small probability relationships because the data set is just way too big.
It reminds me of, I'm not even a big Family Guy person. I've probably only seen 20 episodes of Family Guy, but there's a Peter Griffin quote that I always found very funny, where he said something to the effect of, I have ideas that are so great and so profound that if I even began to start to actually think about these ideas, my head would explode.
Yes, exactly.
And I think what you're describing is something similar to that. The super smart people that have created these large language models, they understand how to grow a model, how to make it get bigger. And they understand, in theory, everything that Justin just explained to all of us about how it breaks words down into embeddings and then uses probabilities to predict what's going to happen next. And it looks at relational relations between these words and letters in almost in 3D space. And it does all of this really well. And there's different forms of compute that have enabled this to happen. But what they're saying to us when they say those things is they can't tell you what it's going to say when you type something into the box. They can't tell you. And no one can tell you what it's going to say next. It's a probabilistic tool that has read a data set that is so big and so huge. Sam Altman, the godfather of AI, if you wanted to call him that, has no idea when you type into his company's box what the thing is going to say next. That's what they mean when they say that, and they don't know why it's going to behave that way. Just for context, I've done research on this. It would take the average human being, if they didn't stop, if they somehow could just stay awake and read 24 hours a day, 365, it would take a human being with today's current large language models 86,000 years of nonstop reading, assuming they can learn everything that they just read, to know what the large language model knows, which is why knowing the relationships between all of these things, no one has 86,000 years to read all this stuff. Therefore, no one can predict what it's going to say back to you next. But I don't think it's a scary thing.
No, it's not scary. It's actually the core benefit of the technology. You wouldn't want to know what it's going to say next because that makes it less creative. That means that it's less conversational. That means if you're using it for applications in business, it doesn't sound like a human. It sounds robotic. Like previous gen AI sounded robotic because it was very predictable, because you could, with a high likelihood, predict what was going to come next. And so, the core benefit of this technology is the unpredictable nature. But if you realize that it's just probabilities of picking words and phrases, and that because we're reinforcing good decisions and some of those happen by accident, you might be reinforcing some weird path to get there. That's all it means. It doesn't mean that it's going to suddenly, take over your computer, and we know the extent of its capabilities today, which I think is an important distinction. Like, we know what it can and can't do as a whole. But in terms of those actual conversations, there's no way to know exactly what it's going to say next.
Yeah. Yeah. I think that's a really great explanation. Thank you for that. Next thing I want to ask you, and if you guys couldn't tell, we're throwing all the hard stuff at Justin. He's going to his back's going to hurt after this podcast. How would you describe tokens? Because I think people hear about tokens a lot, and they're like, tokens, like a Mario token, like you get a token in Mario. Like you get a certain amount of tokens. It's like, what does that really mean? Because like people hear about tokens and usage and all that kind of stuff. How do you understand a token in this world?
Yeah. So tokens, you can kind of think about tokens like words, right? So when you're typing into the box and I say my favorite animal, since we're talking about pets, my favorite animal is whatever. Each of those words essentially becomes a token, right? So my is a token, favorite is a token, animal, right? And then those then become or get related to the embeddings that the model was trained on, because it's been trained on a bunch of texts that contain those words. There's a bunch of stuff with my, there's a bunch of stuff with favorite, a bunch of stuff with animal, right? And then it takes those tokens or those words and like we talked about earlier, it looks at the position of those, because animal, my favorite, is different than my favorite animal. And so it needs to understand that. But at high level, it's really just the words essentially that are being inputted into the box. And then it creates this combined embedding of that phrase that contains all those individual tokens. And then the answer comes back as tokens. And so you can think about each of those tokens as having some number value. Each word, therefore, has some number value, and then it's comparing it to a bunch of other words that have number values. And so that's probably the simplest way to think about tokens, is just the individual words that you're inputting or sending when you ask a question.
Got it. One of the ways that I've seen it described is that, like, when a large language model is trained, it doesn't see sentences and paragraphs the way you and I do. It sees billions or trillions of tokens, and then it learns the statistical relationship between them, like which word tends to follow another word. And it basically builds a very large probability map of language. And if you and I were going to read everything, we would understand it in a completely different way. We're reading line by line, sentence by sentence. We're not understanding what we're reading and the relationship between the patterns and the words in math. We're reading it as language. It just still comes back to this thing that, like, only living things understand language. We have made the machines feel like they understand it, but they don't. Next question that I have for you on these topics. So we talked about tokens, we talked about embeddings, we talked about all that kind of stuff. I am curious, like, we've talked on this podcast to people about, like, hey, upload a document, upload your insurance plan from work and ask it questions. When you do that, what's to stop the thing from hallucinating? Like, what changes when you tell it, instead of going to all of your training in the history of all the things, look at this insurance plan and tell me what my deductible would be if I got this procedure done? How does that change things?
Yeah,
for LLMs?
really good question. Really good question. First of all, when you're talking about tokens, I was thinking about, it's kind of like LLMs read things kind of like the old speed reading courses, where it's like, just scan the page with your finger and you understand the general relationship, right? You're not reading line by line. Like LLMs are basically speed reading at a much faster rate than humans ever could. So that's kind of one way that I think about it visually. But so what you're talking about is, and we've mentioned it high level, is RAG, or retrieval augmented generation. And there's actually like 15 different ways to do RAG now. There's like agentic RAG and this type and that type. And so I don't want to go too deep into the details there, but think about what it essentially does is you're changing that relational 3D space to be a smaller box.
Uh,
So when you upload a document, instead of and there's some degree of general knowledge that the LLM will still use if the probabilities dictate that that should be the case, right? Because all of the truth of humanity isn't going to be in that one document. But what it does is it basically narrows in the box that it's emphasizing, and it says, I want you to look at relationships that fit in this box primarily. So if you attach a PDF about your company policies or about your, insurance policy or whatever, and you ask a question about that, it's going to look for those vector relationships or those spatial relationships in that much narrower box now. So instead of searching every fiction novel that's ever been written and every weird Reddit post and every, whatever else, it's saying, okay, hold on. I want you to start by looking in this box. And if all the information you need is in this box or all the relationships exist here, then just use those relationships. And I only want you to look outside of that if you can't find statistical matches. Then we can start to look at everything that we know and try to find words that are similar. So it's basically putting a magnifying glass or a telescope on a much smaller subset of embeddings or language, and it's trying to find the answer from that smaller subset.
Got it. Okay, cool. So it's like if somebody said to you, how many magnets are there? That they just stopped. How many magnets are there?
I would have so many questions.
There's a lot of magnets in a lot of places. Like, where are we? Like, whatever. If somebody said to you, how many magnets are on that refrigerator right now? You'd be like, 3.
Exactly.
Right? So it's like, it's when it's really wide and really broad, it's going to pull from all different places. Or you could tell it, hey, I want you to focus on this refrigerator. Notice I said refrigerator. I didn't say fridge. I didn't say anything weird with my people may tease me about all these weird terms I use from being from New Jersey. So I said refrigerator and I pronounced it correctly.
You did. You did pronounce it correctly.
It's right here. How many magnets are there? Oh, there's 3. And it's basically like you can tell the large language model where to put its focus and where to get its source of truth from. Now, that source of truth, this is an important distinction for people, I think, is the document that you pointed it to or the website you pointed it to. So it is going to go there for its facts, but that website or that document doesn't have everything about the relationship of words ever done, right? So if you said to a large language model, you're not allowed to use anything you've ever learned that you were trained on the general side of things at all, and just go to this document, it probably would spit gibberish back out at you. Wouldn't really make sense. So it uses this, it's smart enough to use this thing for the facts and then use what it knows about the relationship of words and language to say, this is the facts that I found in the thing. And it's going to use its general training of language to communicate back to you what the answer is. So it still uses some of the generalized stuff that it has.
Yeah. And you would want it to, because to your point, it would probably be gibberish otherwise. And if you didn't give it that narrow box and asked about magnets on the refrigerator or the fridge or whatever, the ice chest or whatever you call it, then I guarantee there's a band that has multiple bands that have magnet in the name. I know there's some movies that have magnet in the name. And now you've opened up a realm of possibility that it might give you an answer that's not even about magnets as you know them, but about some magnet movie that exists that was created in some random place. So that's where, using RAG and actually giving it context does reduce the chance of hallucinations because you're grounding it in a narrower space. And that helps it answer some questions that are a little bit more, to Matt's point, truthful about the context that you're giving it. And I know we want to get into some image stuff and video stuff, which is super cool and an extension of what we've already talked about. But I like your questions today. These are good. I don't know if you have any other ones for the people at home.
These are just off the cuff, as this podcast always is. We just are like, hey, let's talk about this, and then we just go. But these are just some of my questions that I had that I wish I had a nice podcast that could have given me the answers to these many years ago. And by the way, the reason I go with the magnet example, I've been thinking about magnets a lot. It's a really weird sentence. I think it's patently absurd that human beings, we walk around every day not thinking about how crazy magnets are.
They are really crazy.
If I go like this and drop these cards, they drop, they fall, they just go down. Like, that is just gravity and physics as we've always known it. And I know magnetism can be explained through science, but it turns science on its head. Everything we know about physics, if you just so happen to bring these two things near each other, it's like, oh, trains can technically levitate if you put two magnets and called it a hyperbolic train, and the train doesn't actually touch the ground. And everyone's like, yeah, it seems about right. It's just magnets. It's not actually floating, but it is floating.
It's crazy. Yeah.
Magnets are kind of crazy. We should start a whole podcast on magnets, and it would just be for my benefit because I'm fascinated.
If there are any magnet enthusiasts out there, definitely send us a message, Yeah, honestly, electromagnetism and that whole subset of physics is fascinating. And physics was not one of the subjects that I was particularly proficient in school, but I was fascinated by it. It really is crazy when you go down the rabbit hole. And then when you get into theoretical physics and all these, ulterior dimensions and stuff, there's some pretty fascinating things happening in the physics world for sure.
Bore our podcasters with this, but I'll pivot us to where we need to go here, which is, okay, we talked about how text works, and I understand how text works, but I genuinely, folks, have no clue how the image generation stuff works. I'm going to make some assumptions here for a second, and then tell me where I'm wrong, and please educate me. I would think that they took images, they meaning the people who trained large language models, and had people, human being trainers, describe in text what is on the screen, or maybe use like crude old school machine learning things to like say image equals cat, image equals basketball. And then have people come over the top and do that reinforcement learning and be like, yeah, that's a Spalding basketball and this is a Rawlings basketball or whatever. And they gave it words to describe it. And then the words get turned into embeddings, and the embeddings are technically tokens. And then it does math stuff. So are they just turning images into text and then turning text into math and then doing the same thing?
Kind of.
Okay.
And so this is where it gets pretty bananas if you think about how image models were actually trained. And so I'm going to focus on diffusion, which was kind of it was really like the first segue into image models, and it's still one of the processes that's used very heavily today. And this is one of those things that I had no idea how it worked, and I went down the rabbit hole one time, and I'm so glad I did because it's crazy. So they trained it on pictures, right? So just like you train traditional large language models on words and written content and whatever, they trained these diffusion models on pictures. And so they would upload a bunch of pictures. And then what they actually do, I don't know if anybody, Photoshop users or even in Canva, where like you can add a blur to an image, like how there's like a Gaussian blur effect and you can like blur out certain things and whatever. So diffusion models were trained by taking existing images and adding a little bit of blur at a time, And they started to actually add a bunch of noise to the images by blurring it more and more and more and more and more until it's just this unrecognizable blob of pixels. And then the model tries to recreate the image from the unrecognizable blob of pixels. And those are essentially embeddings in the image world, right? So you gradually add all this noise. And then at each step, the model is trying to predict the noise that was added. So it's using these neural networks, which are kind of the underpinnings of large language models. So we don't need to go too deep down the rabbit hole there. But it's trying to predict the noise. And then what happens is it starts from random noise, and then it unblurs it little by little to create the image. And so what you're trying to do when you train these models is you blur a picture, and then you create a bunch of different variations of the same picture, right? And that becomes reinforcement for the model. And the noise is generated from the text that you type into the box. So if you think about how we talked about the tokens before, they turn into embeddings, and then we're finding these relationships between words. What they've done with these image models is they've associated these embeddings with random noise in random space. And so what happens when you type, I want a picture of a brown fox on a snowy mountain or something. It takes all of those word embeddings for the thing that you asked, and the models have now correlated those words with these random blurred pixels that they created from breaking down existing images. And what it does is it just starts to slowly unblur the image based on those initial words that were typed into the box, and then it unblurs and reveals this image. And you can have a bunch of different variations of it because there's a bunch of different types of foxes that could exist on this wintry mountainside. And so the more specific you are, the more precise those initial pixels become as it then unblurs your picture and creates your final image. It's also one of the reasons, if you have done image generation with any of these tools, it's really hard to recreate the same thing or even have it change just one feature of the image and like keep everything else the same, because it's doing this blurring and generation process every time. So for the same reason that you can't predict what word will come next, there's really no good way today to just take an image and change one thing about it using AI. Like, it kind of works, but kind of doesn't. And it's because of this diffusion process, if you will. And so I don't know if that blew my mind when I was like, wait, they're just blurring these things until they're unrecognizable and then unblurring them. But that's basically how it works.
That's so cool. I definitely did not know that at all. And I love that. So it's still using math though, right?
Mm-hmm.
Yeah. Okay.
Yeah. So the tokens that you type in are mathematically correlated to like blurred pixels, basically. So
Yeah.
it's just throwing all these blurred pixels onto a canvas and kind of creating the image from there. So the math correlation is between the words that you type and the pixels that it's been trained on, and then it uses that to actually create the final image.
So I'm assuming we can extrapolate, and obviously I'm not using blurring, but I'm sure we can extrapolate this to all generative forms of media. So that also means video and then audio, because the audio stuff is also crazy. So let's say like when they were training large language models on audio, is it safe to assume that like they fed it like the sound of like a trombone, and they fed it the sound of like someone who sings soprano, and then they gave that a description, and the machine gives it a value, and then they show it all other different permutations that sound slightly different but are still technically soprano, and it starts to create values just like that, and it just knows what that tiny portion of a sound is, and that tiny portion of the sound has a numeric value that goes many decimal points past like 1 point, and then like probably 10,000 zeros. So you can get super specific and stitch all this stuff together into what sounds like music. Is that kind of how that works?
Yeah. And if you think about sound, we actually know a lot more about sound than we know about a lot of other mediums, right? Because all sound has a frequency, and my voice has a specific frequency. This is my production background coming out, but if you actually do like sound editing for a video or music or whatever, you're looking at frequency ranges. So your voice has a frequency range over, the possible hertz that are available. And there's different spikes on that frequency range. And if audio editing tools like Adobe has Audition or whatever, you can actually look at what's called the spectral frequency of a sound. And it's basically like a heat map of all the frequencies over that whole range for that sound. And those are all numbers. So we actually have a tremendous amount of mathematical data about sound already, because it's inherently just numbers on a scale. And so in terms of reproducing sound, if you think about what we were talking about with these word relationships, it's actually a lot easier to create sound because it's already math. We can get into frequencies and sound and all that stuff, and that's a whole deep science STEM topic. But at the end of the day, sound kind of starts as math. And so it's a little bit easier to find those mathematical relationships if you're trying to reproduce music or voices or whatever.
So cool. Definitely did not know that either. Makes a lot of sense when you say it though, because as humans, we've already turned sound into math before LLMs. We didn't turn text, to my knowledge, pre-LLM, at least at this scale, into
Definitely not at this scale. Yeah.
Yeah. Like little tiny embeddings and probabilities and values with relationships. So that's so cool. Okay, cool. So I want to ask you one more question I think is be good. Like it's not exactly how this stuff works, but I think it probably is another area that a lot of people listening to this who don't know how it works and now they do they're probably a little bit insecure about. People talk about like GPUs and compute a lot. And that's kind of like the hardware side of how you can do these fantastical large data set mathematical equations quickly. What would like the need to know about that world to sound educated on this stuff?
Yeah, I think it's a really good question. One last point that I want to make about image and video generation before I forget, because this is an important distinction. We talked about word relationships as being 3D space. If you think about image generation, video generation is basically turning that 2D relationship of images into 3 dimensions. Because if you're doing image generation, you're in 2D, so just like you're looking at a screen. Video generation becomes three-dimensional because you have to actually create movement or a relationship of movement. Because if a character is walking towards you or walking towards me, that looks different visually. So so video is a lot more complicated, and there's some different companies doing different things there, but it's because you're now looking at three-dimensional space essentially. But with GPUs, so a lot of people are familiar with this talk track when crypto, and the crypto industry is still growing or whatever, but people have heard of Bitcoin. And then there was a lot of stuff about like, well, these Bitcoin miners are using all these computers and it's taking all this energy or whatever. And it seems like a weird comparison, but essentially Bitcoin operates with computers doing really complex math equations to validate transactions. And we don't need to go down the crypto rabbit hole. But if you think about it, to solve those complicated math equations, you need pretty powerful computers because it takes a lot of processing power and energy to do so. Like if on your computer today, you open up 40 different applications at the same time, it's probably going to slow down because you think about how much computing resources each of those applications takes, right? And so when you're solving these really complicated math problems, you need a powerful computer because it takes a lot of energy for that computer to do that thing. And so when you look at training models or refining models, and to your point, this 86,000 year data set now that you've trained ChatGPT on, creating all of those embeddings and creating all of those relationships and creating this database of information, this giant vector database of words and relationships, all of that takes a lot of computing power. And so you need to have giant warehouses full of servers and computers in order to do this. If you look at the average enterprise company, a lot of them have giant warehouses full of server, like Amazon, to process all of your orders and your order history or whatever. They have a bunch of computer towers that are running at all times to manage all of that information.
Right.
And if you think about training LLMs, that scale is even larger to a degree that's hard to imagine because of the amount of data that's going into it and the amount of work that needs to be done to create these relationships. So these companies need to buy a bunch of computers. If anybody's ever played video games and you built like a gaming laptop or whatever, you wanted to get a really good graphics card so that you could render all the images in the games you're playing. So those graphics cards are GPUs, and that's one of the primary pieces of computer hardware that's used in these processes to actually train these models. And so that's why companies are investing a ton of money into building a bunch of these computer warehouses. They need to buy a bunch of GPUs that are specifically made to be powerful enough to do all of this really complicated work at a very large scale. And that's why all these companies are buying GPUs. NVIDIA happens to be a company that made one of the leading pieces of hardware for this application. And that's why their company valuation has gone up a bajillion times in the last couple of years, because it's a finite resource that is needed to create computers powerful enough to do all of this stuff that's happening behind the scenes to actually train ChatGPT or Claude or any of these other models.
Got it. The way that I've always understood GPUs, like started in the gaming community, as you alluded to, and then it's basically like, it can, for lack of a better word, do like task decomposition. Like think of like a CPU in a computer as a classic part of a computer many of us have heard about for decades. It's something that can work pretty linearly on big tasks, and it's going to this is my understanding of like the hardware side. Tell me if it's correct. Think of it kind of as a linear thing that can work through like a big task, and it is the sole worker of that job. More powerful than any of the mini workers in the GPU. But I understand that GPUs are like a series of like 1,000 workers all going to work on a task in their little portion of the world, but they all do it at the same time.
Yeah. Yeah. And what you could also think about is, for anybody who's spent time in computers, like Intel was one of the first companies to make like quad core CPUs for computers, which meant that all of those linear tasks, you could now run like 4 linear tasks at the same time instead of 1. Then there was like 16 cores and 30. There were so many cores on computers recently, right? Yeah. Which just means that you can do all that stuff in parallel. And so GPUs allow you to scale those really intensive processes and to your point, have like a bunch of power going into this one thing. And the way to take it back to something I said earlier with training these models, where that the transformers unlocked being able to train a bunch of stuff at once. That's kind of like what those early multi-core CPUs allowed computers to do, is now you can do a bunch of different stuff at the same time instead of just opening like Microsoft Paint and trying to draw, like something and then your computer crashes like it used to back in the day.
That's awesome. I think this is a great place for us to wrap up. I don't know how practical this information will be for people to know in their lives, but I bet you anyone who listens to this podcast, thanks to you, Justin, and thanks for letting me grill you with 21 questions, is going to feel a lot better that and generally I kind of know how that stuff works. And I think that should make people feel a lot more confident with it and also to speak to it and hopefully less doomsday about it, honestly, because when you know that this thing doesn't really understand language the way you do, it just feels like it does. That should give people a lot of comfort that you can use the benefits of this tool and you don't have to worry about it taking over. Computers are still math equations. They're ones and zeros.
Yeah. And the things we can do now are way more powerful than we could before. But at the end of the day, it's the same computer language it's always been. It's trying to predict what comes next. And it knows what it's been trained on. And the reason it seems so powerful and scary is because we were now able to train it on 1,000 years worth of content. But at the end of the day, it's just finding relationships between words, or with images, it's finding relationships between pictures that it's already created. And the last point I'll make is, we've talked about this part before, a very non-doomsday point is human creativity. Image generation models, video generation models make some really cool things, and they're great tools, but they're recreating things that they've been trained on. They're not actually creating anything new. It seems like it's new, but in reality, it's a combination of all of these things that it's been trained on in the past. So genuine human creativity, coming up with something truly unique, truly different, truly new that's never been done before, that is still a very uniquely human action, because these models can't actually build completely new things that it's never seen.
Yep. We have the novel creativity. It can stitch together a bunch of different things that have happened over the course of time. But yeah, we are still the only living things can do things that are truly novel and unique. And we should just use these things for what they are. Same way we've always used a computer. Computer's a tool. It's really powerful. If I wrote an equation in Excel and I know that I need to repeat it over and over, I'm going to click and drag that as many rows as I need. I don't need to do each one. That's a tool, right? I knew how to do the general formula, did it right once. I checked the math. Cool. Now I'm clicking and dragging 300 rows. No need for me to do all that. No need for you to do, if you wanted to make a song for somebody's birthday, no need for you to learn how to play every single possible instrument. You can go prompt it and it's okay. So Justin, seriously, thank you. I learned a bunch on this podcast. Hopefully our listeners did as well. Do us a favor, everybody. We need you to like the podcast and subscribe to the podcast. Guess what? Do you know, before we can even make a penny from YouTube, 1 penny for this podcast, we would need 3 million views. That is correct. You heard that right, everyone. 3 million views or 1,000 subscribers. And we want to do this as long as we possibly can to make sure that we can make this as helpful for everyone as possible. And you, by watching or subscribing or telling a friend to subscribe, check it out. It helps, and it's free for you to do so. So please help us keep the podcast rolling by getting us one step closer to those 3 million views.
Yeah.
See you in 2030. It's going to take a minute.
Yeah. Get us those views. And my final request before we sign off would be, if there's stuff that you are interested in learning about, or there's questions that you have about AI or AI tools, or something that you read, something you don't understand, shoot us a message, comment on one of the episodes, let us know what you want to see next, because we would love to talk about things that are genuinely interesting for you. That's what I'll leave you with.
Yeah, we're here for it. So thank you, Justin, and we will see everybody next time.
See you next time. Bye, everybody.